Hey there, everybody. This is Math 35, College Algebra at College of the Sequoias. This is our second session. This is on a review of real numbers and operations. Stuff many of you are familiar with, but there might be some new stuff in there for you. This is in R2. And it's the real numbers and their properties. So real numbers, we like to use it. For real numbers, we have a symbol. It's a capital R, and then we draw another vertical line on the R, and this is how we indicate a real number. And in the whole notation that we had, it's all elements X such that X is a point on the number line. What does that mean? Well, let's draw a number line. Let's take a look at it. Good starting point is 0, but we have 1, 2, 3. We can have negative numbers. We could have any point like -1's a real number. We could do something like 2.5. 2.5 is a real number. It could be something crazy like square root of 2. Square root of 2 is, I want to say it's about 1.4 if you throw it in the calculator. Square root of 2. So lots of things have it. Things that qualify, any decimal or fraction does. The square root of any positive number. Or exponents. Square roots or exponents. Like 2 to the 4th power, we'll cover that. And it doesn't just have to be square roots, any root works. You'll see other roots as we're going through the class. So that's what we indicate as real numbers. We talked about the other day, natural numbers. They have a symbol also. We use a capital N, and just like with real numbers, we put an extra vertical bar. So we've got N like that. And recall, this was all the whole numbers starting at 1. Speaking of whole numbers, let's take a look at whole numbers. They include 0. So it's like the natural numbers, but add the 0 in. We have integers. Integers, there's no fractions or decimals, but we can use negative numbers as well. So ... -3, -2, -1, 0, 1, 2, 3, ... Keep going in either direction. We have rational numbers. And there's a lot of overlap here, if you can tell. Well, rational numbers has the word ratio in it, and a ratio is a fraction. So fractions count in this. And decimals, both repeating and terminating. Terminal. Repeating is like where it's like 0.111111111, and it keeps going. It doesn't have to be the same number. It could be like 0.123, 123, 123. As long as it keeps going, that's repeating. Terminal, you run out of numbers. We'll cover how to write those numbers in a second. Hit pause if you need to have this up a little longer. All right. We said rational numbers. Maybe let's talk about our other things that have the word rational. And then we've got our irrational numbers. And the best way to really describe this is it's any number that is a real number, but not rational. This has decimals in it. But they neither repeat nor end. Some common ones, pi, called pi. It sounds like the word pi, or it's spelled like the word pi, but without the E. It's approximately 3.14. That means approximately. It's a wavy equal sign. But it keeps going. If you put pi in a calculator, I can grab mine and put mine up real quick. Mine only shows, 9 decimal places. Pi is an unending number. In fact, they have contests every March 14th. Several places in the country that have recite as many numbers of pi as you can. And I've seen people do like 500, like memorize 500 numbers in a row. It's fucking crazy if you think about it. Crazy. Another famous one that you may not be aware of, we actually use the letter E, English or American letter E. I better change that to approximately. It's approximately 2.71. This shows up in nature a lot. This also irrational numbers include anything that's a root but doesn't have like result in a number. Like square root of 4 is 2, but square root of 2, 3, or 5, throw them in a calculator, they just keep doing stuff like that. And then our final category is imaginary numbers. And imaginary numbers have an I in them, and we give the symbol I, and I has a value. It's equal to the square root of -1. If you throw this into a calculator, it's going to say error because it's not a real number. That's why we call it imaginary. But it does show up in a lot of mathematics that actually affect your life. Alternating current, what goes through our households and keeps our power on, our AC running, our television working. Very science behind that requires imaginary numbers. It's crazy. So maybe, I don't know that imaginary is the best word for it because it makes it sound non-real or like it doesn't exist and doesn't have a purpose, but it does. So there's several different number things. If you look at them, we'll cover more of that later. Let's keep going. So more in this section, we have stuff called algebraic expressions. You'll sometimes see it say variable expressions. So algebraic expressions combine both numbers and variables by basic arithmetic operations. I'm kind of crazy. Sometimes my t's, I put a little curve on them like the typewriter. And sometimes I don't. It's a bad habit. I need to stick with one or the other. I tend to put the curve on it because a t without the curve on it looks like a plus sign. And sometimes we use t for a variable, often like time. We like to use t for time. And if time is variable, we don't want to have just t sitting there because it looks like a plus sign. So I got used to doing the t. As a reminder, basic arithmetic operations include addition, subtraction. This is the symbol we use for multiplication in math. I know in high school and below, they tend to use an X, but the X we use a lot for variables, and it's easy to get confused. We're going to use multiplication. It's a dot, and it's not down below like a period. It's in the middle. We can also do division, and algebraic expressions also include exponents and roots. All right. If you need it longer, pause. We're going to go. The show must go on. We've got more information. There's a lot of info here. Exponential expressions. Sometimes abbreviated exponential. They have an exponent. And so let's just give a little example. Let's say we've got 2 with a 3 elevated above. Here, the 3 is the exponent. The 2 is called the base. And what this really says is take the base and multiply it by itself that many times. So 2 times 2 times 2. And if we multiply that out, it equals 8. So some very exponential expressions, we don't even need the exponent. We can rewrite it without the exponent. The general formula, let me get you used to using letters. When we use a letter that can take on any value, that's a variable, and we can use any letter or symbol that we like that isn't used elsewhere. We like to use a lot. So like if we have a to the n power, this is a times a times a times dot 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 times a, and there will be n a's, n number of a's. And we use some terminology for this. We will say a to the nth power. And sometimes math people are very lazy. I'll point out several times how we're lazy throughout this course. Sometimes we drop the word power and we just say a to the nth. If it's the second power, we have a to the second power, we say a squared. And this comes from the area of a square. A square has equal sides. If I call each side a in length, the area is a times a. And that's why, since it's the shape of a square, we say a squared. Another common one is a to the third power is a cubed, because it's the volume of a cube. Cubes are like three-dimensional squares, like dice, six-sided dice are them. That's a pretty good 3D square. They all have the same dimension or length on each side. So a high, a wide, and a deep. And the volume is a times a times a. which is a to the third power, and that's why we call it a cubed. Any questions? All right. Of course, there's no questions. There's no one in the room that you can't even ask. If you have a question, come on Zoom, email, holler at me. You got my text numbers. Send me a text. Any questions? I feel like I'm in my room. That's funny. Let's take a look at order of operations. This, you will see Facebook posts on this all the time, and there's always people on there. Most people don't remember how to do it. It's really sad because it's something you learn early on, and everybody forgets. But it's essential to all of mathematics. So they commonly use the acronym Pemdas. P-E-M-D-A-S. I tend to like to write it like this. And the reason why this is the order they occur in. Oh, wait. That went on screen pause. What happened? Let me reboot my camera real quick. Pause the video. Pause. All right, we resumed recording. This is the page we were on. And so it has order of operations. We're talking about order of operations. It's abbreviated PEMDAS. It's an acronym. I tend to write it vertically like this with MD on the same line and AS on the same line because this is the order that they happen in. The first operation we do is parentheses. And this includes other grouping forms like brackets or things like that. E is for exponentials and roots. And the reason why we say just exponentials, we can write roots like square roots. We can write it as an exponent. It's going to be a fraction in the exponent. You'll see in the course of the semester. I put MD on the same line because this is both multiplication and division. And then AS is addition and subtraction. For each of the multiplication, division, and addition, subtraction, if it's on the same line, like multiplication, division, they have the same priority. And we go from left to right. And people don't understand why we do this. It's to make sure when we write it, everyone knows what everyone else is doing. If everyone write it in different ways and meant different ways, no one would be able to use anybody else's work because it would mean nothing. So we came up with a common thread, just like language. Everyone uses the same word, the word brown for the color brown. But we do this order and we keep this order of operations so that everyone that uses it knows when you see it, this is what it's meant. Okay, so I know when I was in school, people taught me when I was a student, young kid, they said, remember it as please excuse my dear Aunt Sally. The P, the E, the M, the D, the A, the S. But you know what? I don't have an Aunt Sally. This isn't all that helpful for me. But you know what I have? I have me a dumbass sibling. So please excuse my dumbass sibling. That has P, E, M, D, A, and S. Sibling is brother or sister, in case you don't know. Lots of us have sisters or brothers, and so this is something everyone can remember. And we all probably think our close kin is stupid. When I said parentheses, grouping symbols, the grouping symbols, we got parentheses, we've got brackets, absolute value signs. Sometimes the curly braces, but we try to avoid the curly braces because it means set notation. And these can be nested. They say nested, which means one set inside the other. And when we have that, we start on the inside and work outwards. Start on the inner group. Then work outward. Exponents and roots are also done left to right. This usually is not a problem, but it's worth pointing out. And the reason why we have multiplication and division as the same priority, or addition, subtraction as the same priority, is they really are very much related. And what I mean by this is dividing by 2 is exactly equal to multiplying by 1/2. One half or 1/2. Sometimes people do the horizontal bar like that. Sometimes people do this /, and some people use a vertical line for a 1, or you might see like the typewriter version. Sometimes I use this just to make sure it doesn't look like an I or an L. I think it's a little bit clearer. 1/2, when you take a number and you flip it over like this is the reciprocal of 2. We'll cover reciprocals more later, but just hit you with some info now. Pause and take the notes you need, then we'll do some examples. Okay. Actually, before we do some examples, I'm gonna give you a little table that you might want to have at least some of them memorized. Let's take the numbers. Let's go from 1 to 10. No, 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And if we square the number, we're really multiplying it by itself, which is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. And we keep doing this process, and these are the numbers we get. We could look at x cubed. These ones are often handy to have memorized. 8, 27, 64, 125, 216. This is 343. 8 times 64, I want to say is 512. Yeah. 9 times 81 is 729, and 10 times 100 is 1,000. Now, yeah, some of these later ones are harder to remember, like a little harder to remember. To recall. But the rest of them, these are all double-digit numbers, which are on our times tables. 125, the reason why it's fairly easy to remember is our money system uses quarters, and this is like $1.25, 5 quarters. The rest of them are a little harder to remember, but they're handy to remember because, as you'll see later on, sometimes we'll see the big numbers and we want to rewrite them as something like cubed or squared. So even if you just write it out and have it like on a piece of paper on your wall or something while you're working, handy to have memorized. But hopefully at least familiar. And if you don't memorize them, maybe recognizing 343, I know it's something. If I see it, I know it's something. I can go look it up. So let's look at some examples. Let's do some work. We've thrown a lot of technology or terms around, but we haven't done any math yet. So let's do some math. Let's start off with let's start off simple. Basic order of operations problem. Let's do 12 divided by 4 plus 3 squared times 2. Why don't you pause the video and try to work that out? And then unpause it when you're ready to see the answer. This is an excellent way for you to try learning. If you don't try to do the problems and just watch me do them, you're really not helping yourself at all. I see it a lot of times in class where students are lazy and don't do it or don't try. Not being able to do it and not trying are two different things. The first time you see something and work with something, it's difficult and you may not be able to do it. But if you don't even try, you're doing yourself a big disservice. So at least try. If you get it wrong, you get it wrong, but then you learn something from it, okay? Okay, I'll assume you paused. What I like to do is I like to write down PEMDAS and go down the list. I don't have any parentheses, so I'll cross it off. I do have an exponent. 3 squared is 9. And I will copy down the rest of the problem without editing it. And then that covers all the exponents, so that's gone. And then I've got multiplication and division. I do it from left to right. 12 divided by 3 is 12 divided by 4 is 3. We still have plus 9 times 2. We're not done with multiplication division. We've got another one. So we've got 3 plus 9 times 2 is 18. That finishes that one. And finally, we only have one thing, adding and subtracting. We'll add, and that gives us 21. It's helpful to write the lines down step by step. When you get comfortable doing it, rather than doing this as 2 steps, I would do 12 divided by 4 is 3, and 9 times 2 is 18. And you can bypass the middle step, but that takes practice. You don't want to, you got to get used to working with the system. Okay. Let's take a look at another one. I'm going to have 7 plus 2 cubed divided by 9 minus 2 times 3. When you see something like this with a big fraction like this and a bunch of operations on top and bottom, what you want to do is treat this like they have invisible parentheses in terms of order of operations. So this, I didn't draw the parentheses there at first, but they were added in. And what does that mean? We'll do the order of operations. We start off, we do the exponents on top. 2 cubed is 8. And we still got 9 minus 2 times 3. And now I can do, I've got, if we have our Pemdas, when you have parentheses, you're going to follow all of the rest of the things EMDAS inside the parentheses and then go onward. So I need to do everything on top and bottom before I do this fraction part. That's what that means. So now we've got multiplication, division. I still got the 7 plus 8. Those don't have any multiplication or division. 9 minus 2 times 3 is 6. Then I can do addition and subtraction on top. 7 plus 8 is 15. 9 minus 6 is 3. Now we're done with operations top and bottom. No more invisible parentheses. When you're down to a single number. One number. And it could be multiple digit number like this. 15 is a big, longer, it's got more than one digit. At that point, then we deal with the fraction bar. 15 over 3 is the same thing as 15 divided by 3, and that's 5. So it's good to recognize that fraction and division mean the same thing. All right, let's keep going. Give you another example. I want you guys to try to pause this and work this one out, see what you come up with. And you may or may not know what to do. And that's the top part. The bottom is 2 parentheses negative 8 minus 5 times 3 parentheses 3. Okay, so when you're going the order of operations, we, again, invisible exponents on top and bottom. Or invisible parentheses on top and bottom, my bad. The first thing we want to do is this right here. That's got an exponent. Negative 3 cubed like that means negative 3 times negative 3 times negative 3. The 3's multiply to 27, and then count the negatives. Odd number of negatives mean leave it as a negative sign. If it's even, the negative signs cancel out and becomes a positive sign. So I've got 1 negative sign, 2 negative sign, 3 negative signs. 3 is an odd number. It's going to stay negative. So that top part is going to be negative. We got the negative out front. That one I didn't deal with. Just addressing the parentheses is negative 27. And then I'm going to do the rest. Just leaving it as is. That covers the exponent phase. The reason why I don't do anything for the parentheses is there's in every parentheses that I have that I can see, not the invisible ones, but every parentheses I see, I only have a single number inside of it. Okay? I'm down to a single number. The parentheses really don't do anything here. Other than the one with the cubed. So these parentheses have no operations. No operations. And what does it mean to have this 2 in front of this negative 8 or this negative in front of this? When you have a negative in front, you could very well treat this negative. We could treat that as negative 1. So I could put it in a 1 right there. You don't need it. Like negative x is the same thing as negative 1x. That's a notation we do. And so what we have, when we have parentheses like this, the parentheses mean multiply by what's outside. let me rephrase that. A number touching parentheses like the 2 parentheses -8 means multiply them together. This is effectively a shorter way of writing 2 times -8. Okay? So we're going to do that. We're going to continue our operations. -1 times -27. We multiply the numbers together. 1 times 27 is 27. And I've got 1 negative sign, 2 negative signs. That's positive. 2 negative signs has the even rule, and we're going to use even. So it's positive 27. So that was the change there. We've still got plus -5. And we can do the multiplication on the bottom. I'm going to bring that minus sign down and put it right there. 2 times -8. 2 times 8 is 16. And there's only 1 negative sign, so this will be -16. And I just put the parentheses to make sure that it's clear the negatives with the 16. You don't have to, it's not necessary. I could have just left it as -16. And then 5 times 3 is 15. Now that finished off our multiplication. Vision on the invisible parentheses. Good to know, 27 plus -5 is identically equal to 27 minus 5. Same thing. So this becomes 22. And 2 numbers with the same sign. Keep the sign, add the numbers. Keep the sign and add the numbers. So 16 is negative, 15's got a negative in front of it. These are both, I could rewrite this as -16 plus -15. Just like I did right here, I took it out of the parentheses, but here I can put it back in. It's easy to see that they're both negative numbers. 16 plus 15 is 31. And we're going to keep the sign as negative. And so we get 22 over -31. We can write that as, we can put the negative on top, -22 over 31. And you'll also see the negative out front of the parentheses, -22 over 31. These two are the most common way of writing it. This is a little weird. It's not that common. We could go on to simplify it, and we'll do that a little bit later, practice simplifying stuff. Let's look at other things we can do with this stuff. Well, pause it if you need to. All right. We can evaluate expressions. And oftentimes the instructions will say evaluate. So example, evaluate, let's see, what do I want to do? -4x minus 2y squared minus 3z if x equals 2, y equals -1, and z equals -4. I put the little bar in the z to distinguish from 2's. Okay, so I will always put the bar in the z. It's not like t, where sometimes I put the tail and sometimes I don't. I will always put the bar on z. We frequently use in mathematics x and y as the two dimensions if we're dealing with something square or rectangular. And if we go into a third dimension like depth, we use z for the third one. The reason why, they're near the end of the alphabet, we like to use x, y, z for variables. And we tend to use ABC for numbers or coefficients. I haven't said what coefficients are. We'll get to that though. What do we do here? Evaluate is replace letters with their values. Letters / variables with their values. So what I'm going to do is everywhere I see a variable, I'm going to put parentheses in. And then I'm going to plug in what I have. The x goes right here, it was 2. The y goes right here, it was -1. And the z goes right here, it's -4. The reason why I use parentheses is if I don't, let's just show it real quick. No parentheses. -3z looks like -3 minus 4. -3 minus 4 would be -7 now. And that's not what this is wrong. So you want to use parentheses, especially with negative numbers. Or if there's anything being multiplied. Even if I left out the parentheses here, if I had -4 and 2, it now looks like -42. That's not correct. Now we'll go through our operations. The first thing we do is there's no operations inside the parentheses. So our next option is, we look at our Pemdas. Please excuse my dumbass sibling. We do exponents. -1 squared is -1 times -1. 1 times 1 is 1, and there's 2 negative signs, makes it positive. This is +1. So now I'm done with exponents. I do multiplication and division, again, left to right. So the first one is -2 times 2 is -4. The rest stay the same. When I have a plus there, we often leave it off, unless we're trying to show it's being added. If we're just showing that it's positive, we leave it off. And then I'm just copying everything down. Our next multiplication division is there. -2 times 1 is -2. Or you could treat the negative as coming down and then just do 2 times 1 is 2. And we still have -3 times -4. We do that operation. These stay the same. And then remember, I could treat this as plus parentheses and put that in parentheses. -3 is the same thing as plus -3. Here, I multiplied these two parentheses and I've got the plus there. 3 times 4 is 12. 1 negative, 2 negatives follows the even rule. Even was positive, and I don't need to write plus twice, so it's +12. And now we add from left to right. -4 minus 2 is -6. Then we've got +12. -6 plus 12 is 6. That's our answer. You have to go left to right. If you don't, here's what happens. Negative 4 minus 2 plus 12. If I do these first, 2 plus 12, the correct way to do it would be add the negative 2 and the 12. And then you could get away with it. If you treated them all as addition, it doesn't matter. The problem is sometimes people will look at these and go 2 plus 12 is 14. And that will give you negative 18, which is wrong. So you're better off going left to right. Or if you write it down as, rewrite it as negative 4 plus negative 2 plus 12. Then you can add them in any order, as we'll see in a little bit when we go over other rules. What did I do here? That should have been a negative 4, which makes this a negative 8, which makes this a negative 8, negative 8. Negative 8 minus 2 would be negative 10. Oops. Answer is 2. My bad, made a mistake. If you saw it, now I want to point this out to you. If you're in an actual class and the teacher does something like that, and he's got negative 4 times 2, and the next line he writes negative 2 times 2, and it doesn't look right, say something right away in class. Too often, students won't say anything. They'll think that maybe they misunderstood something, and guess what? Teachers fuck up too. I made a mistake, and if you make me wait 10 minutes in class, you're just gonna be confused the whole 10 minutes and trying to undo. It's a pain. Say something. You can say it very politely, like, Mr. Jones, was that supposed to be negative 4 times 2? And I'll stop and I'll look for what you're talking about. And if I have to say, where are you talking about? You can point it out. And I'll go, oh, thanks. Thank you. So if you take other math classes, and I know you will since you're in college algebra, this is a good thing. If you have a question like something looks wrong, if something looks wrong, stop the teacher if you can, because you might just be saving everyone in the class a lot of time. That was an unintended lesson right there. So if you need to pause it, please do so. Other things we see, we can see stuff like this. And I'm going to use the same thing. X equals 2. Same values. X equals 2, y equals negative 1, z equals negative 4. I don't have any z's here. I very much want to point out this does not equal 7 minus 2, 5, x plus y. This symbol is not equal. Do not do this operation out front first. Do not do that first. Okay? What we're going to do is we're going to plug in, that was just a quick thing to point out. We go ahead and we substitute our x's and y values in. I had y was negative 1. Let me make that negative 1 real quick. I've got 2 plus negative 1. That's just bringing my x in parentheses and my y in parentheses. I'll do the operations inside the parentheses first. 7 minus 2. 2 plus negative 1, remember, is like 2 minus 1. 2 minus 1 is 1. And then I do my multiplying order of operations. There's no operations left inside the parentheses. So this turns into multiplying. 7 minus 2 times 1. 7 minus 2 times 1 is 7 minus 2. We did the multiplying. And finally, 7 minus 2 is 5. Now you'll see me do this a lot where I do equals, equals, and I'm showing equivalency. That's the same thing as I was doing here, going up, down, starting at the top and going down. But this eats up a lot of paper. When I know I've got plenty of space, I can save some space doing that. Let's give you a complicated one to try. Same values for x, y, and z. Let's do 3x over 2 plus z over 4. Ooh, and then a big parentheses, 3z over 12 plus y. I want you to pause the video and take a second and try to figure out what this value is. And if you get the same answer I do in a second, you're doing good. This is it doesn't get a whole lot more complicated than this in reality. All right, I'm going to assume you did, and I'm just replacing all the variables with parentheses right now. And now I'm going to sub them in. Everywhere I have an x, I'm going to put a 2. That's right there. Everywhere I see a y, I'm going to put -1. That's right here. And everywhere I see a z, I'm going to put -4. That's right here. So something that you might recall, I don't have to do 3 times 2 is 6 and then divide by 2 and get 3. If you have numbers on top and bottom and multiply together with fractions, numbers occurring on both top and bottom and there can be no addition or subtraction on top or bottom. In this case, we can cancel it out. What I mean by that, 3 parentheses 2 over 2, I can cancel out. There's no addition or subtraction. I can cancel these out. And this is, when you cancel, you leave behind ones. 3 times 1, and it really just goes away. These go away, and I'm left with a 3. So that first term right there, the 2's cancel, and I've effectively got 3 times 1 over 1, but multiplying or dividing by 1 does nothing. It just leaves the number the same. This is 3. I could do the same thing with the 4's. -4 over 4, I can cross off the 4's, leaving behind a 1. I now have 1 divided by 1 and a negative sign. This is -1. So -1. If you do this operation here, I've got 3 times -4 is -12, and then over 12. 12 divided by 12 is 1, and we've got a negative. That turns into a -1 right there. And finally, y was -1. That addresses all the multiplication and division. And then you can add top and bottom separately. 3 plus -1 is 2. -1 plus -1 is -2. And this simplifies into a nice little, we can put the negative out front. And 2 divided by 2 is 1. And that's our answer. We evaluated, and that's what we got. Okay. Pause it if you need it. Keep going. I've been using X's and Y's and Z's. You can use pretty much any symbol you want for a variable. As long as it's not a math symbol. Like you don't want to use a plus sign to represent a variable. Plus means addition. I've used, honest to God, and I'm not religious, so that's just an expression. I've used a smiley face. I've used frowning faces. I've used a lightning bolt. I've done this, but I even did it on a test when I was a student at COS. I did it on a test because I got tired of using X's. And the problem didn't come with a variable at the time. It was a word problem. And what I did is I just put the smiley face down and I said what the smiley face equals. Smiley face equals this. And I used it. And the teacher wrote a little note like, you're crazy, but this is correct. So you can use, as long as you denote what the symbol means. Okay, you got to write down what it means. Let's talk about the properties of real numbers now. I told you about we could do addition in any order. This is one of those properties, but it's not the first one. And some of these, you are going to go, no shit, Mr. Jones. And it comes up later on. If you're going to be an engineer, you're going to do a lot of stuff. You'll get to like linear algebra and stuff, and you a lot of proofs and stuff like that. And these properties come into play quite a bit. So let's look at let's set up some rules. We're going to say we're going to let A, B, and C be real numbers. Any real number. Negative numbers, square roots, decimals, anything we want. That's our given information. Given information. Our rules. Rule number 1 is called the closure rule. Since both A and B are real, then under closure, A plus B is real. A minus B is real. A times B is real. We don't say, we're missing one, right? I did plus, minus, multiply. We don't say A divided by B is real because B can equal 0. And we know we can't divide by 0. That's a general rule. That's our first rule. Our second rule is called the commutative property. And commutative has, it looks like the root word commute. If you commute to work, you move around, you travel a distance to do it. Commuting means that things can move. A plus B is the same thing as B plus A. And A times B is the same thing as B times A. And not true for subtraction or division. Okay. Ready for another rule? Good. I'm glad you are. Let's do another rule. The next rule is called the associative rule. So this is rule number 3. They don't come in any general order. I'm just numbering them. Help you keep track. We can have A plus B plus C. We can add B plus C together first, or we could add A plus B first, and we get the same values. So it doesn't matter which, as long as everything's being added together, it doesn't matter which ones you add first. If you throw a subtraction sign in there, it screws it up. The same thing applies to multiplication. I could multiply B and C first, or I could multiply A and B first, and the result is the same. And the reason why I've listed addition and multiplication on all of these, something you may not know, multiplication is just repeated addition. Repeated addition. 3 times 2 is like saying 3 added together 2 times, or 2 added together 3 times. Both give you 6. So since it works on addition and multiplication is just repeated addition, then the multiplying stuff works. That's not something you need to know, but it's an interesting fact and helpful. Let's keep going. We've got the identity rule. Identity property, and I'm going to use this symbol. Recall that the backwards E like that is there exists. So there exists that's what the same symbol means. There exists a unique number, unique real number, and in this case the number is 0, such that A plus 0 equals 0 plus A, which equals A. When they say identity, identity tends to mean you start and end with the same value. As a general rule, that's what they mean by identity. So that's the addition one. Can you think of what might be a multiplication identity rule? What rule can we use that would give us the same starting number and ending number if we had multiplication? What do I need to multiply A times to end up with A? 1. So the other identity rule is there exists a unique real number, in this case 1, such that A times 1, which equals 1 times A, equals A. Okay. That's the math thing, why we don't put ones. 1 times A is the same thing as A. But I can translate this to you in real life, in real language. Have you ever said you drove 1 car to work or 1 car to school? You rode 1 bike to school? You took, no, we don't. When it's one of an object, we say A. I drove a car, or I drove my car. I drove the car. Not I. Anytime there's 1, we don't mention the quantity. Let's just think about it. When I ate a candy bar, not I ate 1 candy bar. All right. More rules. Inverse, the inverse rule. And here our unique number is -A. And there exists a unique number such that A plus -A equals -A plus A, which equals 0. And we can translate this to multiplication as long as we apply the rule. If A does not equal 0, there is a 1 over A such that a times 1 over a equals 1 over a times a, which equals a over a, which equals 1. I've never added this step before, but I think it's handy. It's very handy to recognize we can take the numerator, and if it's a 1 on top, put it on top and make it like this. And it's also handy to take, if you've got something on top, you can pull it out and make a multiplication if you leave a 1 on top. That's the inverse rule. And what I was saying, I could do the same thing as this. X over 2 is the same thing as 1/2 times x, which is 1/2 x. That's why I bring it up right here. It can be pretty handy to recognize. Okay. Our next rule, we've got distribution. And here we've got a times b plus c is the same thing as a times b plus a times c. And here we can actually have a negative in there. If we have a negative in there, this is the same thing as a times b minus a times c. And one more, and this might seem trivial, but we have the multiplication of property of 0. Zero times a number is the same thing as the number times 0, which is 0. Wait, we were using a, b, and c, so maybe I should change this to, let's make this a b. Tired of using a, so let's make this a b. 0 times b is b times 0, which equals 0. This seems trivial or like a no shit thing, but is important to solving quadratic equations. And we'll bring it up later. It's one of the main ways we solve quadratic equations. Quadratics have square terms in them. So let's look at some stuff we can do. Pause it if you need to. We could have something like 4/7 times 14x. And I can, instead, this is 14 times x. Using that associative rule, I can say this is 4/7 times 14, and the x is on the outside. And when you have a whole number like this, I'll do it over here. I can rewrite that 14 as 14 over 1. It's still the same value. Now, what that means is 4 times 14 over 7 times 1, x. When you have two fractions multiplied together, you multiply the top, which is called the numerator, and the bottom, which is called the denominator. Top and bottom are shorter to say and easier to write, so I use top and bottom a lot. That's effectively what's going on. We could multiply 4 times 14 and then divide by 7, but let me show you something that's helpful. Write out what multiplies to make 14. Two numbers that multiply to make 14 are 7 and 2. And now I can go through and I've got a 7 on top and a 7 on bottom, and the only symbols are multiplication. I can cross off 7s, replace them with 1s. And now I have 4 times 1 times 2 on top is 8. On bottom, I have 1 times 1 is 1. And 8 divided by 1 is just the original number. So this is the easier way to do this by hand. I can do this by hand relatively quickly, and I don't need a calculator. If I want to do 4 times 14 divided by 7, that's a pain in the butt. It ends up being 56 divided by 7, which is 8. But 4 times 14, not everyone has memorized. 7 times 2, you do though, well, hopefully. What else can we do? What else does this apply to? We could have 5 plus 4 plus x in parentheses like that. I can regroup it like this, put the parentheses around the numbers. That way I can add the numbers together. And I get 9 plus x. And remember, the commutative property means we can change it around. By the commutative property, we can put x plus 9. And as we'll go over in I think another section shortly, we tend to put variables first, and there's a reason for it. Next example, we've got negative m minus 4n. I can distribute this negative. Remember, this is like having a negative 1. And when I distribute it, I get negative 1 times n, technically plus negative 1 times negative 4n. We do the multiplying. Negative 1 times m is just negative 1m or negative m. And negative 1 times negative 4 is positive 4 plus 4n. An operation that we tend to do, I'm going to show you some just basically, and we'll do a lot more of this later, factoring. Factoring is a lot like distributing in reverse. So if I have 4x plus 20, this is the same thing as 4 times x plus 4 times 5. And rather than distributing the 4 times something, I'm going to pull the 4 out. I pull the 4 out, and what does it leave behind? X plus 5. So 4x plus 20 is the same thing as 4 times x plus 5. And you can see that applies by distributing it out. I like to draw little arrows when I'm distributing. I do. 4 times x plus 4 times 5, 4x plus 20. Let's take a look at number lines real quick. Only a little bit more. Number lines. We mentioned them earlier. So if I've got like 3 numbers on there, and without putting what their values are, A, B, and C, higher values or greater values are to the right. Values. And on the left, the further we go left, we have lesser or lower values. So here, this is telling us A is to the left of B. A is less than B. And the way we draw that symbol is A. This is less than. We use it so often, we use this symbol for it. These are interchangeable. That's the less than symbol. And I could also compare C and A. C is greater than A. And that has the symbol going the other way. So is greater than and this are the same thing. So our symbols are, that means less than or is less than. That means greater than. You will see it sometimes like that, or they tend to make the bottom line flat. This is how I do it. This is less than or equal to. And we can do it where it's going the other way. And I'm just going to do the flat one because that's the one I tend to do. Greater than or equal to. Now, if you've ever played Pac-Man, there's a handy way of doing it. I like to, I could treat this like Pac-Man. And Pac-Man goes after food. Goes after the bigger meal. He likes power pellets over regular pellets. That's an old game, I know. But we don't have to restrict it to Pac-Man. We could, why not? We could do Miss Pac-Man, right? And what do they do to make Miss Pac-Man? They just put a bow on it, Pac-Man's head. Fun. And another thing I like to do, another way of remembering it, I'll put teeth on it. It's like an alligator mouth. Alligator wants the bigger food. So if we have one more thing in this area, if A is less than B and B is less than C, we can write this as A is less than B is less than C. The and we can sandwich it. Almost done. Bear with me. Okay. Absolute values. We mentioned them earlier. Let's use them or talk about them. Absolute value. One of the definitions, and probably the most helpful one. The absolute value represents the distance from zero on a number line. Now, I've heard there are some math people that hate that description, and I think they might just be being a little anal. I think for the average person and for most people that use absolute value signs, this is sufficient. And the way we denote it is we put vertical bars around it. And so what do I mean by this, the distance from zero? If I go 3 steps to the left, this is a distance of 3. Or if I go 3 steps to the right, it's also a distance of 3 from 0. So the absolute value or distance from 0 of -3 equals 3. And that's also the same thing as the absolute value of the distance of +3. Recall, if you, well, maybe not recall, if you never thought about it, distance is always, the math term is non-negative, but in reality, distance is always greater than or equal to 0. That's the special math jargon right there. So the easiest way to remember it, easiest approach, if all Pemdas operations are done inside, use the positive version of the number. The actual way they like to describe the absolute value of A, this is the other math lingo. The absolute value of A, let's go back to B. Absolute value of B, I don't like A because it looks like I tend to make it look like a 9. It looks like a sloppy 9 when I get it. The absolute value of B has 2 values. It equals B if B is greater than or equal to 0, and it equals negative B if B is less than 0. And here's a way of looking at it. Let's say B equals negative 2. That means B is less than 0, and the second rule applies. So I've got negative, B was negative 2, so I'll plug it in. And negative times negative, remember 2 negatives cancel out, make a positive, positive 2. And see, we ended up with the positive values either way. Pause it real quick. All right. Absolute value properties. R2 is a long section just because there's so many basic, this is like covering all the math you learned through 5th grade, 4th grade or something like that. Maybe even a little bit higher. So properties of absolute values. The absolute value, I've already told you this one. Distance is always greater than or equal to 0. We just illustrated using a number, but we could do negative A is also the same thing as the absolute value of positive A, which is just A. I went back to A, look at that. Maybe I'll put a little curly tail on it so it looks more like an A. We can throw some math operations in there. The absolute value of A times B is the same thing as the absolute value of A times the absolute value of B. And since multiplication is like, or division is like multiplication of the reciprocal, I can do A over B is equal to the absolute value of A over B, absolute value of B. A rule that does not really come up all that often. You might use this in proof someday in like a higher level math when you get there, but that's a long way down the rabbit hole. And they'll remind you of it then. The triangle inequality, the absolute value of A plus B is always less than the absolute value of A plus the absolute value of B. And we could put the less than or equal to in if one of these is 0. The equal portion would give us a 0, or equal. The 0 for one of the numbers would give us that. Let's look at doing some evaluate. Let's just do a problem or two with this. Let's evaluate And we're going to treat for these problems m equals 13, n equals -9. Our first problem is the absolute value of 3m plus 5n. We're going to replace our m and our n with values in parentheses. Three times 13 is 39, and then I've got plus 5 times -9 is -45. And 39 plus -45 is -6. When you're adding together two numbers that are opposite signs, subtract the smaller number from the bigger number and keep the sign of the bigger number. So 45 minus 39 is 6, and then the bigger number is negative, so we're going to have that, -6, and then the absolute value is 6. Why don't you try the same thing with 2m minus 3n all over m plus n, and I got the absolute values in there. Pause it, try to give it a go, see what you get. Okay. I got 13s for m's and -9s for n's. This is the absolute value of 2 times 13 is 26, minus 3 times the absolute value of -9 over 13 plus -9 is absolute value of 4. That is 26 minus 3. We do the absolute value sign first. That becomes +9. When you take it out of the absolute value signs, you can make a parentheses positive version. 3 times 9 is 27, so we've got 26 minus 27 over 4, and we end up with -1 over 4, or -1/4 with a negative out front. One final thing that you might like, this is just helpful. Just helpful. Let's just have 2 points on a number line. I'm going to use B and C. Let's call this point P and point Q. The distance from Q to P or from P to Q. When we do it, we end up subtracting. The way to do distance when one of the numbers is not 0 is we're going to do distance is absolute value. So we can do Q minus P. You take the bigger number, subtract the smaller number. And that's the same thing as the absolute value of P minus Q. The distance should be the same thing either way. The reason why is, like, let's take this side. If I multiply it by 1, this is like having a 1 in front. Invisible 1. I can write that invisible 1 as the absolute value of -1. This is just cool math jargon stuff. And when we had two absolute values together, we can multiply them together, multiply the things inside together. So -1 times Q minus P. We'll distribute. -1 times Q is -Q. -1 times -P, there's two negative signs, so it's positive, and 1 times p is p. And then remember our commutative property, we can rewrite this as p plus negative q. We can change the order of addition around. But p plus a negative number is the same thing as p minus q. So I just proved to you they're equal. I proved they're equal. Neat, huh? And what I was saying real quick, one last note, adding two numbers with different signs. I said it, but I didn't have room to write. Two numbers with different signs. Subtract smaller from larger. And use the sign of the larger. (26) plus negative 27. Is that the one? The bigger number here, the larger number is the 27. That makes that the smaller. So we'll do 27 minus 26. We get 1. And then the sign of the bigger one is negative. So we'll slap that on there and we get negative 1. Oh, wait, I don't want the circle around that. Get rid of the circle around. That's it for R2. I'll get R3 maybe a little bit later. I got to do something with some people in another Zoom meeting for a little while. And this is going to take some time to process. It's a long lesson, but actually the homework assignments aren't that long. This is a lot of going over rules that you probably know most of the rules already, hopefully. Hopefully this rings some sort of bell for you. Peace. Talk to you guys later.